So good afternoon, everyone, and welcome to this webinar organized by the FIB Young Members Group about the development of tsunami loading equation for bridges superstructures using OpenSees and PFEM. My name is Marta Del Zoppo, and I will co-chair this webinar together with my colleague Nicola Tosic from the Young Members Group board. So Nicola.
Yes, hi everyone, and really thank you for joining, what I'm sure will be a very, very interesting and exciting webinar to hear a lot of interesting things from our panelists. So first, just a few kind of housekeeping rules. Please change your Zoom name so that we can see your surname and name and be able to identify you. Where you were informed that the webinar is being recorded and it will be shared on the FIB social media channels and its YouTube channel. The panelists are only able to speak during the webinar, so please use the chat and Q&A for any questions that you may have during the entire duration of the webinar, and then we'll go through all of them and direct them to our speaker at the end. So yeah, please keep this in mind. And regarding the, let's say, webinar itself, it's of course completely free of charge, your attendance, but you are eligible for a certificate of attendance if you attend at least 60% of the webinar. This is tracked, let's say, automatically. If you need a certificate of attendance, then please contact the FIB Secretariat on this email address on your screen. And let's say the fee for that certificate is 10 Swiss francs in case anyone needs it. So just a brief background about what is the group that is organizing this webinar, and it's the FIB Young Members Group. So the FIB, besides its, let's say, main work through its commissions, task groups, work on the model code, has one group dedicated to engaging with young engineers, both researchers and practitioners. And this is another important, let's say, the FIB is the bridge between research and practice, but the Young Members Group is, let's say, a bridge between students finishing and entering their careers and a more senior stage of their professional life. So this is a kind of group to join young professionals, something that was noticed by the Secretariat and the Presidium as missing. And since 2017, there has been first a kind of international Young Members Group, a kind of, let's say, general group that is then guiding national groups in organizing their own national Young Members Group. So the idea is to perform activities through these specific national Young Members Groups. So in your country, you can contact us directly or your national FIB group and find out if there is already a national Young Members Group. If not, we can be in touch and help you to get organized. The idea is to be a kind of professional network and organize activities. So different activities range from visiting construction sites, visiting, concrete plants, visiting different companies, discussing FIB publications, and promoting the FIB work in general and the activity of young members within the task group. So it's also a kind of conduit into entering different task groups. You can find more information on our social media profiles. So there's a Facebook page, LinkedIn page, and on the FIB website itself. Within commissions, if you go under the panel, you will see on the bottom Young Members Group, and there is a contact form so you can be in touch with us directly. So a lot of activities around all FIB symposia. If you attend any, for example, the Congress in Oslo now in June, the PhD symposium in Rome this year also, there will be representatives there and we can talk. So this webinar itself is just one in a long series of webinars that we started during the pandemic, and now let's say we are continuing in a kind of interesting series of lectures. So you'll see this one later available as well. I think from my side that's all. If anything else, also through the chat and Q&A, please feel free to write.
Yes. As the FIB, we have also some working group and task group and commissions beside the Young Members Group one, like the one about the design and assessment for tsunami loading. So recently we started this task group with Professor Tiziana Rossetto from University College London. So if you are working on tsunami loading or assessment for tsunami of existing assets or new design of buildings in tsunami exposed areas, so you can wish to get in touch with us and work together with us on our activities in this task group. You can find all the information on the FIB official website. And now it's time to introduce our speaker of today, is Professor Michael Scott. Michael Scott is a professor of structural engineering at the School of Civil and Construction Engineering of the Oregon State University in the USA. He's a part of the team of developers and maintainers of the OpenSees finite element software framework, and is also really his research and teaching interest arise with a nonlinear structural analysis, and also the dynamic behavior of structures, and also object-oriented software design, parallel computers, and of course numerical methods. So today, Professor Michael Scott will talk about the development of tsunami loading equations for bridges superstructures using OpenSees and PFEM. So please, the floor is yours, and thank you for joining us.
Thanks again, Marta and Nicola and FIB, young members group, for the invitation to present. So what I wanted to talk about today is kind of a brief overview of the development of tsunami loading equations for bridge superstructures using OpenSees and PFEM. Okay, so this was part of a project over the last few years within some of the departments of transportation in the US, and just kind of want to present some of the outcomes and methodology behind these loading equations. Okay, so I think, as we all know, tsunamis, just a little bit of background first, literally from Japanese harbor wave is tsunami, but it's caused by earthquakes, landslides, and other phenomenon, natural and even man-made in some cases. But recent tsunami events, within the last 20 years, of course, the 2004 Indian Ocean tsunami, events in Chile in 2010 and 2015, and then the 2011 Japan, Great East Japan earthquake and tsunami. Okay, have really, these events have really, thrust tsunamis into the forefront of structural, civil infrastructure engineering. So it's become a very widely studied topic of late. Okay, but in terms of the US, the last major US tsunami was in 1964 caused by a magnitude 9.2 earthquake in Alaska, but waves reached as far as British Columbia in Canada, on the west coast of Canada, but the Pacific Northwest in the US and Northern California. So sorry for all the abbreviations here, but I should know my audience better. But British Columbia is BC, PNW is Pacific Northwest United States, and NorCal is Northern California of the US. Okay, so too much informal abbreviations there, but at any rate, but within this region of the Northwest United States Pacific coast, right? There's this Cascadia subduction zone, which is less than 100 miles off the coastline of up here in the upper right, Oregon, Washington, Northern California down here, and British Columbia up here in Canada, right? But there's about 100 miles off the coast is the CSZ, but it has the potential for not only a long duration subduction zone style earthquake, right? But predictions are that when that happens, 20 to 40 minutes later, it could be a tsunami that travels, from the fault to the west coast of the U.S. with waves predicted to be up to 30 feet high, and perhaps half a mile or kilometer or two inundation, okay, inland, right? And based on geologic records and oral history from Native Americans, the kind of last major CSZ event, right, was in 1700, and also there was an orphan tsunami in Japan on that date that correlated with or triangulated with all these other geologic studies and oral histories. So the date is nailed down pretty well. But based on previous records, these major CSZ events happen about every 300 to 500 years. All right, so there's about a 10% chance a large CSZ event could hit by 2030. All right, based on one study from about 10 years ago. Okay, so it's a very pressing issue. It's not really an if, but a when, right? Kind of situation. So that's kind of where, or what motivates some of the, or what motivated this research, and then also, when that event happens, it could be a very devastating event because much of the infrastructure in Oregon and Washington was not even designed for earthquakes. So if bridges withstand earthquakes, the resulting tsunami could also, be very devastating. But I mean, just to highlight, right? Oregon had no seismic design code until 1974. Right, it was like earthquakes stopped at the California border, right? But we know that's not true. And of course, much of the critical infrastructure in Oregon was built before 1974. So there's very little lateral load resistance, all right, for earthquakes or tsunamis or whatever the case may be. Okay, so aging infrastructure, new or not new, but hazards that weren't really considered, must be taken into account. Okay, and of course, bridges serve as lifelines for evacuation recovery after an event. Of course, they must be functional after ground shaking and an earthquake, and then also withstand subsequent tsunami attack. Okay, and there's really no major design provisions for tsunamis within the United States, or there were not until recently. Okay, and I want to talk about some of the initial efforts of developing design provisions for tsunami loading on bridges. Okay, but these are images from Japan. Sorry, I don't have the source here, but it kind of shows what can happen to a superstructure, right? So this is the before picture, and then figure B is the after picture where the superstructure was just lifted and carried downstream. Here's an aerial view, right, of kind of where the parts of the superstructure ended up. These are the piers down here, and then here's a more close-up picture of some of the deck pieces there. Okay, so tie down forces, horizontal loads were very significant, right? Okay, so that kind of motivated through PEER, the Pacific Earthquake Engineering Research Center, the kind of original sponsors of OpenSees, which I'll talk about in a few minutes, a pooled fund study and modeling efforts to say, well, can we even model numerically the response of bridges to tsunami loadings, right? And there was a 2014 tsunami modeling workshop held at OSU between US and Japan researchers, shown here on the left, right? And that led to a year or two later, the start of a pooled fund study with all of the Western state DOTs, or Departments of Transportation in the US. So Oregon, California, Washington, along the West Coast of the contiguous United States, and then Alaska kind of up north, and then Hawaii, of course, out in the Pacific, very prone to tsunami attacks from multiple directions. Okay. And the objective of the study was to develop some initial design guide specifications for tsunami loading on bridges. Okay. Okay, so one of the main parts of the pooled fund study, and I'll just spend one slide on this, but we have to develop, or we have to know what's the hazard, right? So a probabilistic tsunami hazard analysis was performed by Pat Lynette and Hanki Theo at USC and RMS, respectively, doing some different triggering events around the Pacific Rim, and then probabilistically looking at what's the kind of like earthquake analysis, but basically to kind of sum it up was based on all these different possible scenarios of, say, an earthquake in Alaska or an earthquake in Japan, and then kind of the convolution of all those things, develop maximum credible flow height and speed at different grid locations along the coast of Oregon, Washington, California, Alaska, Hawaii. Right, so kind of like maximum credible earthquake, right? You can also develop maximum credible flow height for a tsunami, and then flow speed at different locations. And depending on where bridges are and how populated different areas are, there was a grid size of 10 to 60 meters where you could determine what would be the maximum credible flow height and speed at each of those grid locations. So quantify the hazard, right? It's the first piece, right? And then go into for each bridge, develop numerical models based on that flow height and speed to determine the forces on the bridges. So I'll change gears here a little bit and talk about how we do that kind of site-specific bridge analysis, given a specific location, right, and bridge geometry. How do we estimate the forces or simulate the forces that are imparted on the bridge by a tsunami? So what we did, right? So I was kind of given a somewhat high level overview introduction, and now I want to drill down into some of the structural finite element analyses. But we use the particle finite element method, or PFEM, which was developed at CIMNE in Spain by Oñate, Edelson, and other researchers for fluid structure interaction. So the advantage of the PFEM is it uses a Lagrangian formulation, which is very good for earthquake engineering and structural finite elements, because they also use Lagrangian formulation. So the coupling of fluid and structure is almost natural and doesn't rely on a staggered kind of solve the fluid, solve the structure, and two separate systems, and then go back and forth. It's all monolithic, as we say. Okay, but very good for multi-physics problems like FSI, and also can account for large deformation. So Dr. Minji Zhu has implemented the PFEM within OpenSees using a couple of different approaches. First, the moving mesh, and then a background mesh approach, which I'll talk briefly about today. But again, this helps us integrate Lagrange formulation with the elements within OpenSees that people typically use for earthquake engineering simulation. So beam columns, solid elements, all of that stuff can be naturally coupled with FSI or with the PFEM. Okay, so just as a general overview, the moving mesh, which is the original implementation of PFEM within OpenSees, identified structural, fluid, and interface particles, okay, shown here in the figure, and then performed a Delaunay triangulation over all the nodes and all the particles, right? And then created structural and fluid elements based on that triangulation. All right, so this is kind of the resulting Lagrangian mesh that would be formed with the moving mesh. And we say moving because this process repeats at every time step. So you're constantly identifying particles and then remeshing and doing these computations at every time step. And it becomes a little bit computationally burdensome. And also you can get to distorted meshes under, large, like if you can get irregular shaped elements with the moving mesh. All right, so it has some drawbacks. So that, we initially started using this method for the bridge loading, and we saw that there were some limitations. And then so we started looking at some of the newer developments from Simne, from Onyate, Edelson, and researchers. And there was this method called the background mesh, right, which is a little more stable. But what it does is it kind of creates a fixed grid of cells and finite element nodes around the fluid domain. All right, kind of shown here. So these triangle elements and this grid here is fixed. All right, so we're not remeshing, and we're just tracking particles moving through the mesh. Kind of like ALE, but still Lagrangian. All right. But we only need to do Delaunay triangulation around the fluid structure interface, not over the entire domain. Okay, so it becomes computationally efficient or less inefficient, and then it's a little more stable numerically because we're not remeshing and getting distorted elements. Okay, but if we have a fluid and then a structural mesh, like let's say this is like a simple stick model of a bridge deck, right? Like a cross section here, right? With girders, deck there, right? We would, identify the location of the structure and then the FSI area, around, the structure and the fluid, and then remove some of the grid nodes, right? And then triangulate, around the interface only. So these elements here are triangulated, and then the rest of the fluid, like the fluid only domain, remains on a relatively fixed grid. Okay, so that was the approach that we used, or that's the current approach within OpenSees to do fluid structure interaction. Okay, and then finally remove some of the unneeded elements. If you compare this, we don't need these elements across the top here, right? It's just from the boundary, right? And then remove those elements, and we just have a very small moving mesh around the structure, right? And then a fixed mesh for the fluid. Okay, so deep dive into the fluid method, although not that detailed. But then that was the approach we used to model tsunami loading on bridges, right? But in order to have some confidence that we're not just running a bunch of simulations and producing results that we don't know if they're right or not, or not terribly wrong or not, we started by comparing the simulations with some experimental results from the PWRI, or Public Works Research Institute in Japan, who did some experiments soon after the 2011 earthquake and tsunami in Japan. But this was a kind of a schematic of the wave flume. It was 30 meters long. All these units are in millimeters, right? So 30,000 millimeters, 30 millimeters, 1 meter wide tank. All right, and but there was a reservoir, a gate that was released, which caused tsunami downstream on the superstructure. All right, and then different forces were measured at the connections to what would be a substructure, right? And then the resultant horizontal and vertical forces were developed or recorded. Sorry. Okay, so here's kind of a movie from PWRI, but kind of shows the wave impact on the bridge, the initial impact, and then kind of the overtopping on the bridge, right? And then it's not a very good figure, but here we're comparing the horizontal force from the experiment with simulation, and we get the steady state force fairly well. The peak forces are course, hard to nail down, but I think it does a pretty good job in this very controlled experiment. All right, using OpenSees to simulate the experiment. All right, so over here in the lower right is the results of a simulation in OpenSees that you can kind of see at various, every half second. So it looks kind of choppy, right? But you can see the impact and the overtopping over the bridge deck. Okay. So we did one case, it looked good, and we moved on. No, I'm just kidding. We did a bunch of different cases. There were several trials run by PWRI for different wave heights and bridge configurations. I'm just showing you one here, but we did, we looked at all the different cases we could, right, with PWRI, and determined that we did a pretty good job with OpenSees simulations. And these were all in 2D, right? So it's fairly efficient. Takes a couple hours to do each run, but I'm trying to click out of this. Hold on. There we go. Okay, so all right, returning back to kind of the pooled fund study, right? We used that maximum credible flow height and speed from the grid points from the probabilistic tsunami hazard analysis that I mentioned a few slides ago. For every bridge along the Oregon, Washington, California, Alaska, Hawaii coast, where we had information on flow height and speed, use those values to kind of determine, some kind of tsunami bore profile. So we don't want to run, like end-to-end simulations, right, for all possible scenarios. That would just take too long. So what we did was assume a bore profile, put it very close numerically to a bridge. Say this was a bridge, poorly drawn, but we would assume some horizontal velocity profile and some vertical velocity profile for this bore, right, as an initial condition, right up close to the bridge numerically, and then let it go with these initial conditions, right, and then it would flow and impact the bridge, and we would determine the forces on the superstructure. Okay, so that was our approach to do a bunch of real bridges under different scenarios for different flow heights and speeds, right? And then find the horizontal and vertical forces, and also using this kind of simplified approach was also found to be good compared to the experimental data. So it gave us confidence that this assumed bore, right, with horizontal and velocity gradients, was a good representation of the dam break or the full 30-meter kind of end-to-end simulation. So we want to do a bunch of these simulations to look at a lot of different bridges and not spend too much time and effort on that. Okay, so for example, right, this is a bridge along the Oregon coast, along US 101, which runs pretty much north to south along the entire West Coast. But in the Siletz Bay of Oregon, from our, at this location, longitude, latitude, the ocean is out here. Here's a bay, right? So we could get some, significant channeling effects, and based on, grid, different grid sizes, and running different flow scenarios probabilistically, right? But from that PTHA, you can determine the maximum flow height at this location could be as high as 10, incredibly, 10 meters, flow speed 5.5 meters per second. Okay. So, based on the, as-built bridge elevation, we could assume a bore that looks like this, right? Put it right up close to the bridge, right? And then, run, simulation on this bridge for this flow height, and get some, estimate or simulation for the total horizontal force, right? As well as their impact horizontal force, as well as steady state force. So just annotate, right? But, this will be the impact force. And then here's kind of the steady state. Okay. And then for the vertical force, right, you have some initial uplift force, and then if the wave overtops the bridge, which it does in this case, we would have a downward kind of steady state force, if you will, right? The weight of the water is acting on the bridge. So these are kind of the important aspects: horizontal impact, horizontal steady state, vertical uplift, and then downward force. Okay. And again, we do that for a bunch of bridges, bunch of analyses, right? Yeah, and then develop some loading equations. Okay. So we kind of postulated, right, that in terms of horizontal load, based on some work by Mosen, Azenbacht, and Solomon Yim, also at Oregon State, that the nominal horizontal force resultant on a bridge was basically comprised of a hydrostatic component. That's what this first term here is. And then a hydrodynamic component, all right, which is based on flow speed. This U squared is the flow speed, all right, and then H0 is the flow height. Okay, so a very simple form of an equation, but that's what we chose to adjust, based on numerical simulations. Okay, so we took the hydrostatic component and then introduced a factor, just a linear factor C1, and for hydrodynamic, a factor C2 that would allow us to kind of turn or develop a loading equation that would match the simulations with some of the numerical experiments, and I go from there. So if we plotted from the simulation, the horizontal steady state force simulation, and then the steady state force predicted by the unfactored equations, you'd see that the unfactored equations, i.e. with C1 and C2 equal to 1, over predicted the simulation, right? So we could, if we believe, right, that the simulation is an accurate result, which we had reason to not distrust it because we matched experiments fairly well, then we could adjust C1 and C2 to be, in this case, something less than 1, to bring the loading equation more in line with the simulations. Okay. I think these days you call that machine learning, right? But it was the simplest form of machine learning, i.e. linear regression, right? But bringing these points down closer to the 1, 1 line was the idea, okay? So that gave us an adjusted loading equation for horizontal steady state force, all right? And then based on the observed ratios of peak impact forces and steady state forces for horizontal loads, we just, again, kind of took a simple approach and took that nominal horizontal force and multiplied by an impact factor, right, to get the peak horizontal impact load, okay? And that was usually around 2.5 or so. Okay. But like for open girder bridges, we looked at two types of bridges: open girder, you see up here in the upper right, an open girder bridge. But C1 and C2, we got to be 0.75, 0.8. I think the numbers were a little more exact than that, but this is something to be used in practice, right? So telling someone the factor is 0.738 is not good, right? So just make it 0.75, right? Okay, and then the impact factor, 2.1 on the horizontal. Okay, and this was based on some work by Zhanglang Jie at OSU for his PhD in 2019. Okay. Oh, yeah. And then for box beam bridges, okay, and we did a lot of simulations varying the flow height and speed. All right. But we came up with different factors for the box beam bridges. All right, C1, C2. All right, impact is a little bit higher ratio between steady state and impact force, but 2.6. Okay. Okay, and then so that kind of gives the idea of how we came up with the loading equations. For horizontal loads, we could do the same types of things for uplift, right, and downward loading equations, but I won't go through those. But again, it was kind of this idea of taking a nominal component due to, like, for uplift, like impact as well as buoyancy, and then adjusting those factors from simulations. But going into, other factors, right, like super elevation, skew, and slope, which are shown over here. How do we adjust these nominal equations to account for different bridge geometries? It gets very complex very quickly. All right, but some of the work by Dennis Estrade and Ian Buckle at University of Nevada, Reno, they looked at some of the 3D effects, all right, or effects that you can't represent in 2D models. They looked at skew and slope, all right, for flow or tsunami flow around skewed bridges, right, which gave us some different distributions of connection forces at different points on the bridge, connections from the superstructure to the substructure. Also, Dennis and Ian are looking at debris loading on bridges. All right, what I showed was a very easy case of clean water on basically straight bridges, right, which is not reality, but it gives us a good starting point. And then, a very important aspect, of course, is the substructure analysis, like with scour, and just general loss of stability for the bridge piers, or whatever is the connection to the foundation, right? Okay, but the initial design specifications for superstructure loads, right, was approved by AASHTO in 2021. So this will make its way into the next bridge design specifications, and also be further refined with more research and investigation, hopefully between the research team behind this effort, as well as some of the work done or that will occur with FIB and the task group that Marta mentioned at the beginning of the talk. Okay, so a lot more work to do, but I think it's a good start, and it shows some of the power behind OpenSees and the particle finite element method. But it's ideal for modeling tsunami impact on bridges and other structures. Again, and then because the FSI is done in a Lagrangian form, right? All the stuff that earthquake engineers are familiar with in OpenSees can be used for FSI to let us look at sequential earthquake and tsunami analysis, all right, on buildings as well as bridges. And then, of course, debris impact on structures, right, which is, if you've seen any tsunami videos, right, like from Japan, like there's big boats, shipping containers, floating and impacting buildings, right, which or debris can dam in front of a bridge, increase the area of flow catching, all right, that will increase forces on the bridge. All right, so debris impact is a big deal, and it needs to be addressed, right? But again, numerical simulations, we use those to develop some initial tsunami loading equations with credible wave heights, velocities, different bridge geometries, configurations. All right, but really, it's gives engineers a tool to not only design new bridges, but also probably more importantly, retrofit existing bridges to resist tsunami loads. I mean, so some of the discussion, I'll close with a short and little story, but some of our discussions during task group meetings for this project, when you're designing new bridges, well, the key is just, the bridge is here, just build it as high as possible. That's the best defense, right, against tsunamis. But so it's, but that's not always possible, right? But if you could, build the bridge as high as possible just in a tsunami zone. But more importantly, it's about ways to retrofit existing bridges to resist tsunami loads. So if you can retrofit connections to hold the bridge down or prevent it from basically shearing off the substructure, and that's what some of these equations can help us do. Okay, so with that, I think I will wrap it up.
So first of all, thank you, Michael, for the really brilliant presentation. Really interesting. So I see we have already one question in the chat from Jonas Schell. He's a PhD student of Tiziano Rossetto from UCL. So his question is about the possibility to model to capture the nonlinear behavior of composite structures like reinforced concrete buildings. So the question probably is, can we model material component level properties of the structure to this PFEM approach?
Yes, most definitely. So you can, like anything, I assume you're familiar with OpenSees, Jonas, but like the fiber sections or nonlinear or force-based beam column, displacement-based, all of those models can be used within a PFEM analysis. So you can do RC buildings, either to do an earthquake and then a tsunami, or just do tsunami loading on these types of composite structures. It's not a problem, so to speak, or it's all kind of there in one package. It's not a separate thing from the rest of OpenSees. So.
Okay, so basically with this software, we can model the entire inundation. So we can simulate an inundation and see which are the solicitation, bending moments, and shear force in the structure during the entire loading.
Yes.
Okay.
Yes. Yeah.
And this is feasible in, it's not the computational effort is not so easy we're talking about 2 hours or something.
Yeah, to like those the PWRI experiments where we modeled the full 30-meter long flume and the dam break and then the flow towards the bridge. That took a few hours, but that was mostly flow from the reservoir or the tank to the bridge. But it was also 2D, right? And it was a few years ago, right? So computers have gotten a little faster, and but it'd probably still take a few hours. But then 3D type simulations with the PFEM and OpenSees, we're still it's the capabilities there, but of course the runtimes go up by a factor of 8, 10, something like that. But all the capability is there, and we need to keep refining it and improving. So
okay, thank you.
Yeah.
And we have another question.
Okay.
From Mistress Laisia Sentaye Abate. This is really complicated. Excuse me if I'm reading it wrong. So can we incorporate it with the performance-based design methodology, which was developed by the peer in 2001, because we cannot rely on code-based design methodology. So what will be the performance levels of such bridges?
Oh, that's a good question. Performance levels. Okay. So I guess we can incorporate it with performance-based methodologies for sure. But then in terms of performance levels, there's, you could think of it as immediate, kind of like the buildings, right? Immediate occupancy, i.e. for bridges, immediate, travel over the bridge. At the other extreme for buildings, right, we had collapse prevention, but I guess that's for a bridge that would be, don't lose the the superstructure to a tsunami, right? Keep that tied down and not in the river. But in between, right? Yeah, that's a good question. I haven't really thought of it that. I mean, I know we had some discussions about that within our pooled fund study about the different performance levels, but you can kind of map it from repairable within a week, or what's the downtime, right? But it all fits within performance-based methodologies for sure, right? But yeah, the exact levels of performance, I kind of gave you the easy extremes, right? But in between, yeah, it would be based on like the time to repair, or how soon can you get vehicles across the bridge again if it's been damaged but not lost, right? Entirely. So, good question. Good question.
Thank you. And we have also another question in the chat. The question is from Claudia Reis from the Lisbon University. And the question is about your opinion using previously characterized time histories of tsunami pressures and applied them at an infrastructure node, nodes. So for each node, a different time series, if it is possible.
Yeah, I think we looked at some of that initially. So you mean like recording pressure, like in the PWI experiment, like there were pressure sensors on different locations of the bridge or the bridge deck, and then recording those pressure time histories and then using that as input to the model. Is that kind of the question?
Probably yes, because usually, I don't know exactly, Claudia, which kind of work do, but usually when we model buildings, for instance, we simulate the pressure in OpenSees at different nodes of the structure. We simulate load history. So we simulate the pressure history.
Tributary area or something.
Exactly. Yeah. Because we don't consider the interaction. So we already know, also we make an hypothesis about the pressure of the history on each node and then simulate the response. So probably the question is how much this approach can be correct in view of your more refined simulation.
Yeah. I think it's a valid approach. I guess it would kind of miss if you had a very flexible building or something, right? There might be some FSI that would be missed, but I mean, but yeah, it's definitely I think a valid approach. Yeah.
Okay.
But yeah, maybe Claudio, we can follow up afterwards on that. Sure. It looks like there's a couple more questions in the
Q&A. Yes.
The Q&A. Yeah.
From Vasim Ramadan. Excuse me if this might be a naive question, but how do you lift open the gate representing a dam breaking in the tsunami experiment? Because I believe that the way you open the gate would cause differences between the simulation and experiment.
Yeah. Okay. Yeah, that's a good question. Because it does, how you do the gate definitely affects the flow. So like in the actual experiment in Japan, they just, I think, like if this is the gate, I don't know if you can see my camera, but this is the gate, and then I think there was a hold at the top, and then they just pulled that, and then the gate just flopped down, and then the water flowed out. I know in some like numerical, so I mean, you can model that within your software, right? Just make this like some beam elements, right, and have initial condition, and then just let the physics take over. But I know in some experiments, people, the gate is like lifted, like this, or even some like numerical water tank experiments that the gate just kind of disappears, right? Or it's just the water is held as an initial condition, right? And then you just let it go like there's no gate at all, which I guess is kind of like lifting it very quickly, right? But yeah, it does definitely affect the flow downstream. So, but yeah, I think the way we did it was just to model the gate and then as beam elements, and then just let it fall due to the pressure behind the gate.
Okay.
So yeah, good question. Yeah.
I have a question about this. Because now you're simulating this dam breaking test, so you have this kind of input for the water. But if you want to simulate a tsunami, so in a real tsunami, so not replicating an experimental test like the dam breaking or this, how do you provide the input to the water to move like a tsunami with the right pressure, right velocity and water height?
Mm-hmm. Yeah, so like, I mean, the kind of like the approach we used was to get like the maximum credible flow height and speed, and then I kind of skipped over this detail in the presentation, so it's a good question. But we looked at, from the PWI experiments, we looked at the distribution of horizontal velocity and vertical velocity, as the bore was approaching the bridge, right? And then, from that, we kind of mapped out those simplified profiles of horizontal and vertical velocity. So those were based on, tracking the flow during those experiments, or in the numerical simulation of the experiments, and kind of idealizing that as the tsunami flow condition for all the numerical experiments we did on the bridges, later in the project. But so really just tracking the fluid flow and then idealizing that.
Okay, thank you. We have another question from Ida Maitan. So what are the main advantages of PFM compared to other Lagrangian methods such as SPH or MPS?
Yes, I think with PFEM, one of the advantages is, it's Lagrangian, but so are the SPH and MPS, but it's also finite element based, right? So we're creating finite elements for the fluid and the structure, and then the interface. Whereas I believe SPH, and I'm not very familiar with MPS, but with SPH, it's all particles kind of interacting, and there's no mesh per se. So it just in terms of coupling the structural, or a structural model with a fluid model, the PFEM has the advantage of just, it's all like finite element, and not, as far as I understand, SPH is kind of a bunch of particles. And I think you need, with SPH, correct me if I'm wrong, but I think you need a lot of particles to get good results. Like in terms of forces and pressures, which is always tricky. I mean, we can get displacements and velocities pretty well with any of these methods, but I think in terms of kind of the engineering quantities of interest, getting the pressures and forces right, or quote unquote right, is a bit tricky. And I think the PFEM is, and I might just be making stuff up here, but I think it's a little bit better in terms of getting the forces and pressures than SPH, but I need to do a little more homework on that. But I think it just the FEM based aspect is the advantage in my mind, that we can couple structural elements and fluid elements. So, okay, thank you.
Okay, perfect. Thank you. I
Marta,
haven't seen-
there was a raised hand that disappeared by Julian Tambu, but I don't know. Julian, let us know in the chat if you still have a question. There was a raised hand, but then it was lowered.
Okay. Okay. Yeah, and if you have any, if anybody has any follow-up questions or anything, you can find my email online.
Yes.
Just if you Google Michael Scott, be sure to give some qualifiers on that, because you'll end up at the United States version of the Office television show if you just type Michael Scott into Google. So put Michael Scott, Oregon State or something. You'll get to the right place. Not a bunch of pictures of Steve Carell. So.
Okay, maybe we can wait just a couple of minutes more to see if there are other questions. Yes, I also have seen the raised hand from Ajit. I don't know if he's still online. And meanwhile, I have last question for you about the development of this loading equation. Which kind of variables did you take into account to come up with the final equation? So you made different simulations. Which kind of variables did you change?
Well, definitely like the flow height, the flow speed, the bridge geometry, the fluid density, and bridge geometry kind of accounts for a lot of things. But like we kind of looked at, like as you go to like wider and wider bridge decks or more girders, spacing between girders. We looked at the effect of like trapped air a little bit, and that's something more that Dennis and Ian, Dennis Estrada, Ian Buckle at University of Nevada, Reno, did some experiments on that. Actually, if you're looking for a more detailed and in-depth presentation, Dennis would be very good to ask. He did some very good experiments with skew bridges and trapped air. And but yeah, we looked at the effect of trapped air, which is significant on the uplift force. But mostly it was about the flow conditions. And then, the bridge, like the super elevation, and then some of the 3D effects. And, like in terms of small debris, like we just increase the density of the fluid. But we didn't look at large debris, at least not yet. But actually Dennis and I and Ian and Minji are looking at large debris impacts currently on another project. So lots of good stuff to look at.
Yeah, that's true.
Yeah.
Okay. There are other two questions, one in the chat, one in the Q&A. So I start with the Q&A from Theodoros Temede Baza. The equation developed is not applicable for seismic effect on the bridge, right? Seismic.
Right. Yeah. So that would be a separate load case altogether. But I mean, there is definitely some correlation between the lateral load resistance for seismic and as well as tsunami load. Maybe more so in the buildings world, but I think there's some anecdotes that maybe Marta, you can correct me here, but if the building's over a certain height and designed for a certain level of earthquake resistance, it's generally regarded as safe against tsunamis or something along those lines. I may not be saying that.
There is a sort of simplified approach in the AC7 about this simplified check to see if the seismic design is up to a certain level. The tsunami check is not required. Yep.
Yeah. Okay. One more. Yeah.
Yes.
It's probably maybe be the last one. I got it.
Yes, the last one from
late for another
Claudia.
meeting,
Yeah,
yeah.
the webinar was so interesting, so we have a lot of questions.
That's okay.
So Claudia is asking, due to the drag coefficient, I'm thinking, can the equation provide time-dependent results?
No, so these equations that we develop are more just for the peak impact force and then kind of the steady state force, but not. But I guess if you applied the equations, yeah, as like the flow height maybe goes up, and if you had some time series of flow height and flow velocity, you could, yeah, I mean, you could get a time series out of those equations, right? And then compare that to the experiments. Yeah, but that the intent, of course, was just to get the peak values and the steady state. But yeah, I guess, yeah, you could compute them in a time-dependent manner. Not sure how good it would be. It'd be a good thing to try, I think, to see how it works out. But yeah.
Okay. So thank you, Michael, for the presentation and for answering to all these questions. And thank you to the audience for this really interesting question and for staying with us till the end. And for all of you, and also for Michael, if you want to join our task group so we can have a further discussion about all these open issues that we have on this field about tsunami design and assessment, you are more than welcome. And thank you again, Michael. And
thank you.
See you in our next webinars. Yeah. Keep safe and good evening.
You too. All right. Thank you.
Bye-bye.
Bye.